Hi guys, I hope you are doing well. Let's get ready for our first test of the semester. And so I'm going to be going through the Unit 8 practice test here. And so the first question is asking to circle the following compounds that are covalent. So one of the requirements to be covalent is you have to be nonmetals. So any of these that contain a metal cannot make a covalent compound. So sodium and bromine. Sodium is a metal. And so how I know this, recall that if we were to look at the periodic table, which I'll bring up here, that everything that I'm highlighting here are all metals. The gold are metalloids. So we're looking for things in the upper right corner. Sorry, and I did not mean to hit hydrogen here because we have to remember hydrogens are lone nonmetal on the left side of the periodic table. So because sodium lives in the first group, it cannot be a covalent compound. When we have carbon and hydrogen, both of those are nonmetals, so that will work. Magnesium lives in the second group, which is a metal, so that cannot work. Phosphorus and oxygen both live on the right side of the table, so that could form a covalent compound. And carbon and sulfur also are nonmetals. So the three compounds you should have are CH4, P2O5, and CS2. I'm going to get rid of this table here so we can move on. One moment. Okay, so Lewis dot structures. So the next three questions are talking about the differences between Lewis dot structures, molecular formulas, and structural formulas. So Lewis dot, that's when we draw our valence electrons here. So for methane or CH4, this would be the Lewis dot structure. So it's telling us, yes, what elements and how many atoms are present. We know how the atoms are arranged, but we also know how the molecules bonded together. So A is the most correct answer. As for molecular formulas, that would be if I just wrote CH4. We don't know how it's bonded together yet. We don't know how they're arranged. So molecular formulas, they only really show us what elements and how many are present. And now structural formulas, the key here is, yes, we may think that it shows us how the molecules bonded together, but the key here is that it says including lone pairs. Typically with structural formulas, those aren't required like they are in Lewis dot structures. So the most correct answer here is going to be B. Number 5. So we kind of covered this in number 1, it was an application of it, but covalent compounds, they're made of 2 or more nonmetals, not metals. When you see metal and a nonmetal, this is going to be ionic, which we'll talk about next unit. Covalent bonds, they are formed by the sharing of valence electrons. That was the first definition that we talked about in this unit. Is the following a correct Lewis structure for C2H4O? So we have to make sure that there is a octet and that hydrogen doesn't have more than one bond. Those are kind of the two rules here. And so if we're looking at this carbon, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. So that is good. It is satisfied. Now if we look at the next carbon here, we have 1, 2, 3, 4, 5, 6, 7, 8. So that is also satisfied. And then if we look at the oxygen here, that has 1, 2, 3, 4, 5, 6, 7, 8. So that also has a full octet. So the 2 carbons in the oxygen are good. And then again, double checking that the hydrogens only have 1 bond, because hydrogens can only ever have 2 electrons from the shared bond it forms. So yes, that is the correct Lewis structure. Same idea, except now for NH3. And here right away, we can tell it's not, because if we look at this, hydrogen has 3 bonds. Remember, hydrogen only ever makes 1 bond, so that is incorrect. Number 9, a double bond is sharing how many electrons? So we can think of this example here We just went through and counted. Think of each solid line counts as 2 electrons. So a double bond has 4 electrons being shared. Which of the following is the correct set of diatomic molecules? So here we have to recall that our diatomic molecules, remember, there's 7 of them that make a 7, starting with atomic number 7. So there's kind of a lot of rules here that help you remember. But we can't forget that hydrogen is included as well. So if we check the list, the one that has those 7 is going to be answer A. Which of the following correctly shows a prefix used in naming covalent compounds with its correct corresponding number? And so A, right away, deca is 10. Remember, nona is 9, hexa is 6, hepta is 7. So those are not right. All right, on to the next page. During covalent bonding, each element is trying to achieve an octet, except which only wants 2 electrons. So we kind of just talked about this. Hydrogen only wants 2 electrons because remember, it has its 1 valence electron, so it's always going to form one bond with something else. Let's just use another hydrogen, for example. So it will always only have those 2 electrons. Number 13. What type of bond is the following Lewis structure? Well, that is a triple bond because there's 1, 2, 3 lines in between the 2 atoms. This is also an incorrect structure, so I'm sorry for using that as an example. How many bonding areas does the following Lewis structure contain? So bonding areas is just the same as lines or bonds. So it contains 1, 2, 3, 4. Or D. Is the following Lewis dot structure, how many lone pairs around the central atom? So you first identify oxygen is the central atom and it has 1 and 2 pairs. So you're counting them in pairs. Which of the following generally describes covalent compounds? And so again, this is all the way back to unit 8.1, and we talked about that covalent compounds have low melting points. And the key is generally. Obviously, there's always some exceptions. The following covalent compound, tetraphosphorus octoxide, has which formula? So we have to remember that tetra is 4, and then we're looking for phosphorus, so it has the symbol P. Oct has 8, and oxide is oxygen. So we're looking for P4O8, which is A. The following covalent compound, phosphorus pentachloride, has the formula. So if it's just phosphorus, there's just one of them. And then pentachloride means we have Cl and 5. So we're looking for PCl5, and that gives us A. The following covalent compound, dichlorine heptoxide, has the following. Heptoxide. I am screwing up pronouncing the names today. So chlorine, Cl, and di means there's 2. Oxide is oxygen or O, and then hept is 7. So we're looking for Cl2O7, and that is A. The following covalent compound, N2F9, is named. So we have to remember that N is nitrogen. And since there's 2 of them, we're going to put di in front. And then F is fluorine, and nona is the prefix for 9. So dinitrogen, nonafluorine. And so that is, and I'm making a mistake here. Not fluorine. Hopefully you guys caught me there. It should be fluoride. This is the second element. We changed the ending to "ide." So the answer there should be A. The following covalent compound is named. So again, we have 2 of them. So we're using di. And since it's the first element here, we're going to use chlorine. The second prefix is tetra for 4, and then bromide. So we're looking for dichlorine, tetrabromide, that gives us D. Oh, and I circled the wrong one. I wrote it. Sorry. A. What is the formula for the following compound? Nitrogen trioxide. So nitrogen is N, oxygen is O, and if there's tri, that means there's 3. So NO3 or A. Sorry, I'm just realizing there's a lot of A's in a row here. Don't let that throw you off. What is the correct name for the formula P2O5? So we're looking at diphosphorus, and then the prefix for 5 is penta, but since it starts with an O, it's going to be pentoxide. So don't forget the IDE like I have before, and that gives us C, which is spelled wrong. Oh my goodness, this needs some editing. Name the following covalent compound, SF6. We have sulfur because there's just one of them, and then hexafluoride. Should be A. All right, next page. So we're going to use this image to answer the next 5 questions. So molecule A is what type of the following? Well, what I like to do is count atoms. So if we think about our shapes, we have linear, bent, trigonal, I'm going to abbreviate that, planar, trigonal, pyramidal, and tetrahedral. So each of these have a certain amount of atoms that they have. So for linear, if you have 2 atoms, it's always linear. And then sometimes when you have 3 atoms. Bent, we're going to have 3 atoms. Trigonal planar, 4 atoms. Same for pyramidal. And when you have 5 atoms, it's always tetrahedral. Now the key difference is when you have 2 of the same amount of atoms. So for example, it could be linear or bent. The reason why one bends is because it has lone electrons on the central atom. Same thing for trigonal, planar, and pyramidal. The difference here, if your central atom has lone electrons on it, then it's going to cause more of that bend. So looking through to determine what molecule A is, I'm first going to start by counting the number of atoms, which we have 1, 2, 3, I can't really see that, 4, 5. That means it's tetrahedral. Molecule B, we have 1, 2, 3, 4. So we know it's either trigonal planar or trigonal pyramidal. In our case, it's going to be pyramidal because the middle central atom is raised a little bit. Again, that occurs because there's lone pair or pairs on the central atom. So that leaves us to trigonal pyramidal. Molecule C, that is going to be linear because they create a straight line with the atoms. Molecule D has 3 atoms, but it is bent, so that gives us A. And then molecule E, it is the only one left, but that's going to be trigonal planar because it has 4 atoms and the central one is not raised above the others. They're all on the same plane, so trigonal planar. Which one of the following has the lowest electronegativity? So I highlighted the 4 options here. And so if we just look at the 4, carbon is going to have the lowest electronegativity value. So what's the electronegativity difference between hydrogen and phosphorus? So if we highlight those, we're looking at hydrogen and phosphorus. And so they actually have the same electronegativity difference. And so it would be 0. What kind of bond will form between hydrogen and phosphorus? In our case, if they have the same electronegativity difference, electronegativity, then they're going to have 0. Remember, this is the same thing as our END. And so I'm going to put out the range for, remember, nonpolar goes from 0 to 0.4. Polar is 0.5 to 2.0. And ionic is greater than 2.0. So recall, these are our electronegativity differences here. And so 0 falls under nonpolar. So that is the answer to 32 here. What's the difference between fluorine and nitrogen? So if we look at the table now, fluorine and nitrogen. Here we're having 4.0 minus 3.0 equals 1.0. And this falls under polar. So the type of bond that will form is polar, and that's the answer to 34. What's the electronegativity difference between oxygen and sodium? Whoops. So we are looking at oxygen and sodium. So if we have 3.5 minus 0.9, that gives us, what, 2.6? Pretty sure. Either way, it's going to be over 2.0, and so the type of bond will be ionic. Which statement best explains why carbon dioxide is nonpolar? So, looking through these, I'm going to start actually from looking at option D. So carbon and oxygen are both nonmetals. That is not a requirement to be nonpolar because there are lots of compounds that are both nonmetals that are polar. So it can't be option D. Carbon and oxygen have the same electronegativity. Well, if we look, first of all, they don't. But even if they did, this is asking why the molecule is nonpolar. And remember that bond polarities do not determine molecule polarities. Carbon dioxide is a gas at room temperature. That doesn't really offer an explanation at all. So that leaves us with A, which even though I wouldn't have had to go through B, C, and D and tell you why they don't work, I just like to explain some kind of how I reason through tests. But because of this symmetrical, remember that is our key word with nonpolar, because the electron distribution is symmetrical, that is what makes carbon dioxide nonpolar. According to Vesper theory, the reason the outside atoms in a molecule are arranged the way they are is due to the fact that, so we have to remember what this stands for, which is valence, shell, electron, pair, and here's the key word, repulsion. So what's happening is the valence shell electron pairs are repelling each other, no matter if they're in a bond or a lone pair. Negatively charged electrons are going to repel other negatively charged electrons. And so the ones that, or the answer is going to be D. This is exactly stating why the atoms in a molecule are arranged the way they are. All right, so 39 and 40 are using the table to the right to determine polarity of the overall molecule. So if this is CHCl3, I'm going to kind of label this as if it had the element symbols on there. Carbon would be our central. Then we would have 1 hydrogen and 3 chlorines. So, because we have 5 atoms, we know it's going to be tetrahedral. And so the next question is, are all of the outside atoms, so what it's talking about here are the ones that are not central, are they all identical? Well, no. So that means it's polar. And then for the next one here, determining the polarity. So C2H2. This is a linear molecule because all of the atoms are in a line. And so it asks, are the outside atoms identical? Yes, both of those hydrogens are identical, so therefore it is non-polar. All right, and that is the end of this video. Good luck studying, and see you guys later.